Hello, this is Bill Langdon of the Crest Group at UCL. I'd like to talk to you about the paper Dissipative Polynomials at the Landscape-Aware Heuristic Search Workshop at GECCO 2021. So the idea is we're going to take computation as information flow. In other words, we're going to look at computer operations in terms of information theory. Most computer operations are irreversible, meaning from the output it's not possible to infer what the inputs were. In other words, each of the operations progressively loses information. So information at the end of a long sequence of changes is relatively independent of the start point. In particular, if there is an error followed by a long sequence of irreversible operations, then that error may become invisible. It may make no difference to the output of the program. From a GP point of view, what we're going to see is that if the trees are deep enough, then the landscape becomes smooth in the sense that many changes in terms of mutation or crossover make little or no difference to the output of the trees. We can think of information in terms of information funnels. So here we have an example where we're taking two 32-bit operations, such as adding them together, and we generate a 32-bit output. So our two floating point numbers each can contain no more than 32 bits of information. In other words, we start off with no more than 64 bits of information, and we generate a single 32-bit answer, which can contain at most 32 bits of information. So we view the funnel as having lost information, more information entering the funnel than leaving it. In terms of genetic programming, what we're going to do is look at a very simple symbolic regression problem. Binary functions just add and multiply by themselves, give us polynomials. And what we're going to do is to study the GP landscape by uniformly sampling. So instead of allowing the GP to evolve, what we're going to do is study its landscape by sampling from the available programming trees. And in particular, what we're interested in is, do crossovers make changes to the fitness of the trees? So what we're particularly interested in is not the fitness of the trees themselves, but the change in fitness caused by crossover. And we're going to sample our crossovers by simply doing uniform crossover between large trees. And what we'll find is, in terms of number of test cases, then the change in fitness as we move away from the mutation site or the crossover site, it falls monotonically. Whereas if we look at the difference in fitness as we move away from the mutation site, it may go up or down, but in most cases, it will eventually fall to zero. So what we're going to do is we're going to take a GP system, which is just composed of pure functions. In other words, it doesn't have side effects. So much of our argument in terms of information theory would apply to pure functional programming as well. What we're going to say in terms of imperative programming in terms of C or Java is essentially the same sort of argument holds. Is by no means as clear-cut in the sense that the programs are heavily dependent on side effects. But if we view an error as occurring deep within some nested hierarchy of programs, then the error may have to transit many irreversible steps before it can be observed, say before it comes to a print statement. Each of those steps may lose information And at the end of a long sequence of irreversible operations, the bug may be totally invisible. It may have no impact outside the program. In terms of our GP system, then, because we don't have side effects, as is usual in GP, we can evaluate the tree in any order, and the result will be identical. So, in particular, instead of evaluating the trees from the top down, we're going to evaluate them from the bottom up. So on the left-hand side, we have a very small tree, which we are evaluating in a traditional top-down fashion. So we start with the root node, which is drawn at the top there, the root node being the subtraction. So that's labeled 1. The second evaluation step, level 2, is to get hold of the leaf 0.026. We return to our subtraction node, and now we need to find its second argument. But its second argument is actually needs the value returned by the divide node, number 3. That in turn depends on the subtraction node, number 4. And that in turn depends on the multiply, number 5. So you can see we have to go through recursive calls in order to return a value up to our subtraction node, at which point it can perform its operation and it actually calculates the value 0.966693. On the right-hand side, we have the same tree, but we're going to evaluate it from the leaf minus 0.826 and work our way up. So the blue node numbers indicate the evaluation order. We start with minus 0.826, move up to the multiply node, and at that point we need its second argument, which in this case is minus 0.718. And then multiply will then calculate exactly the same answer as it calculated in the left-hand side, except it's calculated in a different order. So the point being, although we could do the calculations in different order, we do exactly the same calculations, and they calculate exactly the same answers as before. In incremental evaluation, what we do is we start with the parent and the child and view the child as being identical except for some mutation or crossover. I'm going to use the same test cases on both parent and child. And the fitness evaluation of the parent and child are going to be identical except for the change code, of course, and any part of the tree which depends on the change code. So if we start and do bottom-up evaluation from the crossover point to the root node, then all we need to do is consider changes along that chain. So if on a particular test case, the change code returns an identical value to the original, then working up the tree, its calling function will also return an identical value in the parent and the child. In other words, once the parent and child become identical on a particular test case, then they will remain identical all the way from that point on up the chain to the root node. And I'm going to skip past this one and the next one just in terms of time. So here we have an example. In red is the original code. The white subtree is going to be removed and replaced with black subtree from the second parent. And the way that we do our evaluation is we evaluate the original code into the subtree in the original code and the subtree from the parent, the second parent. If they were identical, then we could stop. We would know that the evaluation of the mutant would be identical to the evaluation of the parent. Of course, in most cases, they aren't identical. So we trace on up the chain from the crossover point to the root node. And at each point in the chain, we compare the evaluation of the child with the parent, with the evaluation of the parent. So this is another schematic showing the same thing. So we start off by evaluating at the bottom our white subtree and our black subtree. If they're identical, we can stop. Otherwise, we move up to the operation immediately above the crossover point, which happens to be an addition in this case. And the addition will need this to the evaluation of the side. So it needs its second argument. But that code has not been changed. That code will be identical in the parent and the child. So we only need to evaluate it once. So that code is evaluated. Its values are passed to the addition. After the addition operates on values from the new black subtree and the old white subtree, there's a comparison. If they're the same, we can stop. Again, most of the time they're not the same, and we proceed up the chain of nodes towards the root node. But if that chain is sufficiently long, in many cases, the evaluations do become identical. At that point, we know they will be identical all the rest of the way from that point to the root node. In other words, at that point, we know the mutant will have the same fitness as its parent. So here we have an example. At the bottom, the red subtree is new code that's been inserted into this large tree. The chain in color, the nodes there, the size of the nodes indicate how many test cases have been disrupted, and the color of the nodes indicates the amount of disruption in terms of RMS difference. So we start off with every test case being different and being quite a lot different. But as we move further and further up the chain towards the root node, the number of test cases progressively falls. And also in this example, the number of, the size of the difference between the parent and the child gets progressively smaller as well. So we start off with black color indicating a big difference, and we end with yellow, and that eventually fades away to the point where there is no difference. In this example, all the test cases return exactly the same value, and at that point we can stop. We know the mutant, despite the fact we've made a large change, it has a fitness which is identical to its parent. The grey nodes indicate there that the parts of the tree that we don't have to evaluate. So here we have the same information, but as a graph. Along the x-axis, along the horizontal axis, we have the distance from the crossover point, and going upwards, we have the number of test cases which are different. So initially, no distance from the crossover, all of all of the test cases for the child are different from those in the parent. But by the time we've moved 13 nested levels up the tree, there are now 3 test cases where the child and the parent have identical evaluation. And we know that if we progress all the way from that point to the root node, those 3 test cases would still be identical. And in fact, as we do move up the tree, the number of test cases which are different between the parent and the child monotonically falls. And eventually, in this example, we reach the point where all of the test cases are identical, and we can stop the evaluation. I'm going to skip through this one. I wanted to show this one because we're going to look at this example in more detail in a moment. So here we have a large change in red, and then a progressive evaluation along the chain from that point up towards root node, which is at the top of the picture. But you can see in this example, although there's quite a long chain of nodes between crossover point and the root node, eventually we get to the point where there is no difference. And at that point, we know the mutant and the offspring, sorry, the mutant and the parent must have exactly the same fitness. This doesn't always happen. Here we have an example where there's a small change in red, and as we progressively evaluate from that point to the root node, the chain of blue nodes, the chain of disrupted nodes, doesn't terminate. So by the time we actually reach the root node in this example, there are at least one test case where the parent and the child have different evaluations. Again, showing you the same thing in terms of graph. So the red line is our monotonically fall to zero disruption eventually, whereas you can see in the second example, again, we have a monotonic fall in the number of test cases which are disrupted, but it doesn't quite reach zero. If we look at absolute values, then the absolute values here, notice the log scale. So there's no guarantee of a monotonic fall, but you can see in the two examples, the size of the difference between the parent and offspring falls quite dramatically. In one case, it falls to zero, but in the second case, it's not quite zero when we reach the root node. So returning to our first example, what we've plotted here is the whole function, which is in red. So this has had to be rescaled to get everything on the same plot. So red is the overall functionality of our high order function. The straight blue line is the functionality of the subtree we're about to remove, which is simple linear in X. So it's just that diagonal line, whereas we're going to replace it with the purple line, which is actually an 8th order polynomial. Notice that, in fact, the replaced code and the inserted code both have the value 0 at the origin. So we know that at the end of our complete evaluation on test case where X is 0, the evaluation of the mutant and the original code are going to be identical. And we know that immediately. This is a zoom in of the graph I've already shown you. So the subtree in red here is the crossover fragment that's been inserted. We have a chain of blue nodes working up the page, and the white is the code that's come on between the parent and the offspring. And what I'm going to show you is evaluation at 3 different points on the chain of blue nodes going up the tree towards the root node. So here is evaluation. The red line is the new code, and the blue line is the original. And you can see already by the time we've just moved up 3 levels to the addition, the number of test cases where they are identical has increased to 19. So what we know is that on those 19 test values, the mutant and the parent will have exactly the same evaluation. If we move slightly further up the tree, then the parent and the child actually have very similar evaluations. So there's only one line plotted, but it actually is the two of them on top of each other. So the parent evaluation and the child evaluation are almost the same. And on 31 points, they're absolutely identical. Again, slightly further up the tree, the parent and the mutant are, again, almost identical evaluations. And on a fifth of our test cases, which is shown with the blue crosses, they are absolutely identical. And if we were to proceed all the way up the chain after 53 additions and 60 multiplications, then the two evaluations of the parent and the child become identical. And we know at that point, although we made a huge change to our tree, it was sufficiently deep that it actually makes no difference to the fitness on our test cases. Last bit here is I've looked at a slightly different system. It's got slightly more test cases, so we now got 1,501 test cases. And what I'm plotting is, instead of individual falling of disrupted test cases, I'm looking at the average. So this is the average over 2,000 or so mutants. And you can see that that's a pretty good fit to an exponential decay. But to be fair, this is after excluding a large number of mutants where the number of test cases didn't actually go to 0. So this is the special cases where the disruption over the huge number of test cases does actually reach 0 before we hit the root node. But the other cases do have the general trend of falling, but not necessarily with the same exponent. So from a GP point of view, what we can see is that increasing the number of test cases has a relatively small impact on the change in fitness. What we see is that it seems to depend approximately on the logarithm of the number of test cases. What we find is that some mutations are not being totally concealed. Is there some way we can characterize those? Certainly some that we can say that they're shallow, they're near the root node, and that's why they're not concealed, but there may be other cases as well. Similarly, can we characterize the test cases? Some tests seem to be much more able to find errors than others. To what extent can we generalize this to other types of GP? And in particular, if we can come up with general rules for how to test GP systems, would those rules apply to programming in general? Would the disruption that we see in some mutations also apply in software engineering? So just to conclude, in the GP system, deeply nesting the crossover points gives rise to a smooth landscape. Increasing the number of test cases seems to only have a marginal effect. So for instance, going from 48 test cases to 1,000 test cases made the testing only marginally more effective. In other words, it made only a marginal increase in the length of the blue chain going towards the root node. We definitely see that deeper crossovers and mutations have less effect. So we might want to, from a GP point of view, we might want to design our crossover on mutation operators so that they were closer to the root node if we wanted to have a more rugged landscape, or further from the root node if we wanted a smoother landscape. What we also see is some particularly nonlinear operations tend to lose information faster, so they're better able to conceal mutations and crossovers. So we might want to consider that when we design our function set. What we also see is that some testing systems are more effective than others. So here, bigger values of input tend to reveal fitness changes more than smaller ones. From a GP point of view, what we see is with the traditional crossover and mutations, as the trees get bigger and bigger, as the trees get deeper, the landscape becomes smoother and smoother, and there are more cases where the parent and the children have identical fitness. Given that high selection will cause the population to converge pretty quickly, and once the population converges, effectively evolution stops. So essentially, from an information point of view, information theory point of view, the information loss is meaning that disruption doesn't reach the root node. In other words, we're getting a smoother fitness landscape due to information loss. From a programming point of view, the slogan "software is not fragile" is obviously a polemic in the sense that there are cases where you can mutate your program, you can insert a typo and it fails disastrously and you lose your probe going to Venus. But there are many cases where software continues despite the presence of many bugs. And we can view this from an information theory point of view as saying, in many cases, the impact of those errors is progressively lost, is dispersed by all the irreversible steps that lie between the error and the program's output. At that point, I should stop.